yesterday we started looking at direct and inverse variation. We'll be focusing on inverse variation, and we looked at a couple problems that were just very basic problems with no context at all. So let's look at the next example that you have here. So the amount of time it takes a ball to roll down a ramp that is 20 feet long varies inversely with the height of the ramp. When the height of the ramp is 2 feet, it takes about 12 seconds to roll to the end of the ramp. Write an equation that gives the time it takes the ball to roll down the ramp T as a function of the height of the ramp H. Okay? So you've got a lot of words here. What you're looking to pick out is this varies inversely. So you want to see what varies inversely with something else. So the amount of time it takes the ball to roll down the ramp varies inversely with the height of the ramp. So it tells us later that time is T and height is H. So we want to use a T here and an H here. And the good news about this is whenever you set these up, you can write it like this. You can do T equals K over H, or you can do H equals K over T. It doesn't really matter which spot you put your H and your T in. In this case, it says write an equation that gives the time it takes the ball to roll down the ramp. So it wants an equation that will give you time. So it's better to use this one in this case because you won't have to solve it for T after that. So, but it'll give you the right answers no matter which way you set it up. The main thing you have to know is that K right there has to be in the top of the fraction. And so it tells us when the height of the ramp is 2, so when H equals 2, the ball takes 12 seconds to roll to the end of the ramp. So the T is 12. So we need to find that K in here announcement. So to do this, we will plug in 12 for our T, and we'll plug in 2 for our H, and then we're going to solve that for K. So right now we have K divided by 2. To get rid of something divided by 2, we will multiply by 2 on both sides. So K equals 24. So our equation is T equals 24 divided by H. Have questions? Alright, and then once you get the equation, part B is pretty simple. If the height of the ramp is 5, how long does it take the ball to roll down the ramp? So all you're doing here is plugging in 5 for your height. So 24 divided by 5 is going to give you 4.8, I think. Yes. 24 is the K. So 24 is your, like that's the constant that is in the equation. So no matter what numbers you're plugging in, 24 is going to be there. So what you'll do for these problems is you'll use, like they'll give you a height and a time or the two variables that you need. You'll plug those in to find K, and then for anything after that, the 24 will be there in the problem, no matter what they ask you for. So that 24 is constant for the whole problem. It's always 24. And you'll see, like if you do 24 divided by 2, you'll get the 12 that you were supposed to get for the height of 2 feet is 12 seconds. So it'll work for any height that you have for the ramp. Okay, questions? All right, let's do another one. The equation d equals rt gives the distance traveled at a rate r and time t. A says rewrite this formula so that the function gives the time as a function of distance and rate. Okay? So whenever you see this, the function gives time as a function of, what that means is that the equation needs to be solved for t. So if I have d equals rt, right? So I have d equals rt. What would I do to solve that for t, to get the t by itself? Kason? Not quite. We do need to get rid of the r, but what's happening between the r and t? We're going to divide because those are multiplied. So we're going to divide the r, and so that will give us t equals d over r. Okay? All right, and this is another opportunity for me to tell you guys not to drive too fast. So Raleigh is about 150 miles away. How does increasing your average speed affect the time it takes to make a trip to Raleigh? Okay, I want us to look at several situations here. Okay, so the equation, in this equation, 150, that's a distance to Raleigh, right? So that means that our equation here would be t equals 150 divided by r. Okay, so let's just look at what happens whenever we plug in several different speeds. Okay, so let's say that you guys need to go to Raleigh, but your parents won't take you, and you have no ride, so you have to walk. Let's say you walk at 4 miles per hour. Okay, if you walk to Raleigh, let's see here. If we walk to Raleigh, 150 divided by 4, it's going to take you 37.5 hours. So that is a really long time. So maybe you decide that you're going to get a bike. How fast do you think you ride your bike? 12. We'll go with 12. So Coach McCulloch, I think he does things like this, like rides 150 miles on a bicycle. So that would take you 12.5 hours. You can at least do it in a day now. You're going to ride your bike to Raleigh. I bet Coach McCulloch could do it much faster. How fast do you think he probably rides? Like 20? Let's say Coach McCulloch rides his bike to Raleigh. Let's not right this second. I don't want to interrupt his class. I think he's got first planted, so yeah, I think he does. I'm not certain. All right, so Coach McCulloch, he might could make it like 7.5 hours. So that's less than an 8-hour day. So pretty good. But this is probably not the best option here for going to Raleigh. So somebody said we'll take a bus, right? And a bus, I feel like our average speed on a bus is not going to be. I'm going to go. Well, the thing about the bus is they're probably going to have some more stops and stuff. That's going to make it longer. But let's go with like maybe 50 miles an hour. Maybe that'll sort of factor in the fact that you might have to stop in Winston and Greensboro and Burlington before you actually get to Raleigh. So let's go with 50 miles an hour if you take the bus. So now we've got 3 hours. So it's starting to become more reasonable, right? Okay, now sometimes yes, but if you take like a Greyhound bus, you're going to have to stop at places. Plus, I don't really think you can get on the Greyhound bus here. You're going to drive to Winston. You have to ride your bike to Winston first before you can do that. So yeah, you have to. So let's say that somebody finally starts feeling sorry for you, and your grandma decides to drive you to Raleigh. Okay, so your grandma is going to drive you to Raleigh. Yeah, depending on your grandma, my Papa Howard would be like 35, but let's say your grandma's a speedy grandma. Let's say she goes 55 miles an hour. So speedy for. Okay, so now we're at 2.727. Let's change that to hours and minutes. So that's 2 hours. 0.727. How do I figure out how many minutes that is? If I do 60 divided by 0.7272, I get 82.5, which is more than an hour. I don't think that's right. You'll do 60 times 0.7272. Because the decimal's like a percentage, sort of, like a percentage of an hour. So you're going to multiply. So that's going to be 2 hours and 43.632 minutes. Yeah, 44 will be fine. Okay, so we're getting a little bit faster, but notice that, like, up here we were making dramatic differences. We were increasing our speed a lot, but we were making dramatic differences. So let's keep going. Let's say that you get somebody to drive you that's going to drive 60 miles an hour, which actually is probably closer to how fast you're actually going to drive. Because although the speed limit most of the way is 65 or 70, you do have to drive to the highway and you got to stop some. So, 60 is actually probably, for an average speed, is probably pretty close to accurate. It is highway most of the way, though. So now we're at 2.5. So that's 2 hours and 30 minutes. And let's see, I'm going to do 65 first. So 150 divided by 65, we get 2.3076. So that's 2 hours, and if we take 0.3076 times 60, we get 18.5 minutes. Okay, let's say we go 70. If you're going 70, you're probably actually running over the speed limit some of the time because you're, when you factor in getting from here to the highway and getting, so, but you're probably not speeding too much. Okay, so 2.1428, so 2 hours and 0.1428. It's going to be close to 15 minutes, isn't it? No, 8, sorry. 8.568 minutes. Okay, let's do a couple more. Let's say we go 75. I'm going up by 5 just for a reason. So 150 divided, oh yeah, it is. Alright, 2 hours. Okay, let's say we go 80. So, divided by 80, we're going to get 1.875. One hour and 52.5 minutes. Alright, let's say that we go 85. You are begging for a ticket if you ride 85 all the way to Raleigh. Okay, so 1.7647, 1 hour. Okay, times 60. We get 46 minutes. Alright, here's what I want you to notice. Okay, and we could keep going with this. Up here, now I wasn't going up by 5 miles an hour, but like here, this, let's do 9 just to see. 150 divided by 9. 150 divided by 9 is 16.666 repeating hours. So right here, if I increased my speed by 5 miles an hour, and I was going 4 miles an hour, and now I'm going 9 miles an hour, look what a big difference it makes. You go from 37.5 hours to 16.6 repeating, so it's like a 20.8, like almost 21 hour difference, right? If you increase your speed by 5 miles an hour. However, right here, whenever I increase my speed by 5 miles an hour, I'm decreasing my time by like 16 minutes. Alright? And then right here, when I increase my speed by 5 miles an hour, let's see, that's like, let's see, here was like, that was like 16.4 minutes. Here, we're going to increase our speed by, let's see, 43, or time, decrease our speed by 13.6. Here, it's going to be 12.5 minutes. Sorry, our time goes down by 12.5 minutes. Here, it goes down by, let's see, 18.5 minus 8.568. So, like 9.932. Here, we go down by 8.568. Here we go down by 7.5. So going faster decreases the time that it takes you to travel that distance, right? But for every increment that you increase your speed, the amount of time it saves you decreases, right? If you were going to have to walk and then somebody offers to let you ride on the back of their bicycle, and you go 9 miles an hour, that makes a 21-hour difference in how long it takes you to get to Raleigh. So that is a huge difference, right? But whenever you get up here, it is making a difference, but it's making a little bit less of a difference the faster you go, right? So what we see here is increasing, and we're going to write this down, increasing speed decreases time, but time decreases less the faster you go. Okay, so here's my driving warning to you. If you are running late for something, you're late to school, or you're late to church, or you're late to wherever you are headed, going faster will get you there a little bit faster, but not that much faster, right? Here we're considering longer distances. We're talking about the difference in 70 and 75. We're only talking about like 9 minutes on a 2-hour trip, right? Whenever we're talking about, you're only going, like, let's do the same thing. Time equals, let's say, you live 5 miles from school, right? Sorry, great. Let's look at the difference. Let's say you live in town. Let's say you're responsible and you drive 35 miles an hour, which is probably going to be the speed limit. Even if you live 5 miles, you probably don't live in town. 5 divided by 35, you're going to get here in 0.14287. That would be times 60. That would be 8.57 minutes. Let's say that you take the same trip but you run 45. So 5 divided by 45 is going to give you 0.11 times 60. That's going to be 6.66 minutes. So by going 45, 8.57 minus 6.66, you only save yourself less than 2 minutes. All right. Let's say that you live 5 miles from school and you run 55. So 35, you're going the speed limit, you're being safe. 45, you're risking getting a ticket and possibly being less safe. But we're not in the range where like I'm terrified for your life yet. 55 into 35, you're talking about big tickets or hurting someone. So 5 divided by 55, we get this times 60 is going to give us 5.45. So like the difference between this and this is barely more than a minute's difference. And you're risking getting a huge ticket that you're going to, possibly lose your license for if you're going more than 15 over, especially if you're on that provisional license. Plus the possibility of wrecking and hurting somebody, all to be here 1 minute faster. Which is probably not going to make all that much difference, right? And then you could drive safely and you're still only 3 minutes difference, right? So think about that when you're driving. It's an inverse relationship. So going faster will get you there quicker, but not by that much. All right, so whenever you speed, you're decreasing the time it takes you to get there, but especially for short distances like 5 miles, and a lot of you probably drive less than 5 miles to get here, then you're talking, not much difference at all. So there's no need to speed like a wild person whenever you're late, because there's a lot of risk involved, and it's not even going to help you all that much. So there's my lesson, my driving lesson for you. I have lots of cautionary tales here with math. So let's do another problem. Okay, the table below shows the force needed to break a board of a given length. The first thing we want to do is graph the function. So for this, I want you guys to graph that there on your little chart there. So graph those points. So if you're a karate man and you're wanting to break a board in half, then this could be helpful to you, because these are probably all the same thickness of boards here, but the longer the board is, the easier it's going to be to break it in half. So like a couple years ago, we took Hunter to the Dixie Classic Fair, and there was like, in the expo part, there was like a karate booth set up there. They're trying to get you to take your kids there to take lessons, and so they had this wheel that you got to spin, and one of the things you could win was you could get to break a board. And so Hunter was like 4, he might have been 5, He was like 5 years old. So they had this board that was super thin and pretty long, and so he got to break the board, and they held it out, and there's little 5-year-old karate chop broke the board in half. He thought he was the coolest kid that had ever lived and could break anything after that. But it was because it was a really easy to break board. So if you were trying to impress somebody, you could use a really thick board. If you made it a lot longer, it's going to break a lot easier. Just like if you think of like a bridge or like trusses for a building, the longer they are, the further you have between your supports, the weaker it is. It doesn't have as much strength. If your supports are closer, you're going to have more strength. So in this case, you can see if you have a really short 2-foot long board, then it's going to take 15 pounds of force to break the board. But if it's 4 feet long, it's almost half of the force that it takes to break the board. And you can see sort of the pattern that I was talking about earlier. We didn't graph the last one, but each time you increase by 2, the force needed is decreasing, but not by as much, right? The difference between a 10-foot and a 12-foot board, not much at all, right? If you could break a 12-foot board, you're probably pretty close to being able to break a 10-foot board, but you're nowhere close to being able to break a 4-foot board. Let's talk about this function. The domain for this particular function, we would be talking about the length of the board. And so in this particular case, our domain of our function, we know that 12 is the longest board that we see here. We don't go to 0, but we can't actually make it to 0, but we could get smaller than 2 feet, right? So I would say domain for this, and these will be kind of like estimates. As long as you're giving something reasonable, that'll be okay. So I would say the domain is 0, but I'd use a less than sign because you cannot have a board that is 0 inches or feet long because it will not exist. And I'm going to use an L for length, and then it would depend on the particular situation for that upper limit. In this case, we stop at 12. You can have boards longer than 12 feet, but I'm going to go 16. As long as you're putting something reasonable there. Anything that you put there. If you put 12, that'd be fine. If you put 14, if you put 16, if you put 20. If you start getting on up 30, 40, 50 feet long, then, boards like that don't exist. If you put 100, that's probably not a good upper estimate. But as long as you're giving me something reasonable, that'll be fine for the situation. And then our force that is needed, as our, like if we think of drawing in the line here, even though it's not here, what do you guys think is going to happen to the force needed as that board gets shorter and shorter and shorter and shorter? It's going to keep on going up and 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 up, right? You're going to have a vertical asymptote there. Same thing's going to happen on this end, right? So if we had a super short board, it's going to be virtually impossible to break it. So range here, I would just say that the force is greater than 0. I made this look like it goes back up, but it doesn't. This would be continue to decrease right there until it gets to 0. So your range, you got Y values. This right here is going to go up forever. The lowest it could ever be, though, is 0. You can't have negative force to break something for that. Our rate of change, okay? Our rate of change, when we talk about rate of change, we are talking about the steepness of this graph. So our rate of change, if we talk about, or you could think of like the change in the amounts here, what is happening to the steepness of our graph? Is it steeper to the left or over here to the right? It's steeper over here to the left, right? So our rate of change would be decreasing here, right? Our rate of change is decreasing. And on these, I just want to know increasing or decreasing. You can only give me the exact rate of change if it's a line. If it has a slope, it's always the same steepness. And then the end behavior, we're only going to talk about, we'll say as x approaches infinity. Not x. We need a L. Or as L approaches infinity, what does the force approach? It approaches 0. Okay. These are a little more of just interpreting the situation, giving something that's a reasonable answer. I don't love that because I like a right exact answer. These will probably be multiple choice if you see them on the test for these. So that gives us some experience with some of these problems. Let's see, where's my